Good morning. My name is Robert Klar. This is actually a presentation that Scott Miller put together. I'm going to talk about a mission. Scott Miller is the flight software lead on this mission. The mission is the Cyclone Global Navigation Satellite System. I'd like to talk a little bit, give you an overview of what the mission's about. I'll talk briefly about the science and give you an overview of what's involved in the mission. And then I'd like to talk more about the flight software and some challenges that we had in putting together the flight software for the mission. CYGNSS is a mission that's focused on studying tropical cyclones. It's actually a hurricane monitoring mission. It's a little bit of a different approach from the types of missions in the past that have been used to study these types of activities. In the past, many of the missions have used a polar orbiting satellite to take images, and that gives you good images for a period of time. But what it doesn't give you is these storms are very dynamic, and it doesn't give you an assessment of how violent these storms are. We have a good way of knowing where these storms are going to hit ground, but we have difficulty saying how violent the storm is going to be or assess the damage. One of the goals of this mission is to provide enough information to be able to predict this better. The mission does this by using a constellation of small microsatellites that, rather than going in a polar orbit, these are going in a low Earth orbit around the equator. So this gives you kind of an overview of the constellation and the instrumentation that's used on it. The instrumentation that's used is a GPS-based instrument that's used that uses the Doppler effect to determine how rough these patches of the ocean are. This is more of a view of the coverage of the path of the satellites as they go around the Earth, and the type of coverage that you can get in this way. There's a picture of Hurricane Igor on the bottom, and this is actually from the International Space Station, but this is the type of view that we hope to be able to get from CYGNSS when CYGNSS is on orbit. So here are the more specific science objectives. I'm not going to go through these in detail, but for the sake of completeness, I did want to present that information. This is a view of the top-level view of the observatory for CYGNSS, and it's a very small spacecraft. The overall, with the solar panels extended, it's about the size of a person, to give you an idea of the scale of this thing. The electronics are actually housed in the center of the spacecraft. There's a chassis that's roughly the size of a 3U compact PCI chassis in the middle that houses the avionics. Here's a block diagram of the observatory, and you can see that there are actually three main cards that make up the electronics. A power supply and a peak power tracker, which are used to maintain power to the electronics and the sensors on the spacecraft. And then there's a board that was named, they named it the Centaur, because it's actually a combination of the communication subsystem, and it also includes the processor, the main processor that runs the flight software. And then there's a complement of sensors which are used. We have a magnetometer, a small star tracker, reaction wheels, torque rods, and there are a few very coarse sun sensors which are used for sun pointing for safing the spacecraft on board. The communication, the transceiver is S-band, is the S-band based transceiver, so it's very limited in terms of the amount of downlink we have. These spacecraft actually are stacked for launch on a deployment module, which is done. The deployment module was developed out here at NASA Ames. It's responsible for that, but they stack up in a configuration like the one shown, and they're launched together. This is a very small envelope. I believe this is set up for a Pegasus. There's not a lot of room to spare. Okay, getting into the flight software itself, we have a layered structure for our software. For the processor, we chose a newer processor which is made by Aeroflex Geisler, the Leon 3 Spark 8. The GR712 RC is the actual chip. Now, the chip has several built-in peripherals, and it's a dual-core chip. In some ways, it has much more capability than what we need to actually operate the spacecraft. So one of our limits is really power in this case. So we operated the chip in a way so as to conserve power. I'll talk a little bit about that as I get into it a bit more. The layers of our flight software, we have a set of device drivers that are tied into the operating system. In this case, we're using RTEMS, is the operating system that we're using. We have a set of middleware that we call a flight core, which is really a message passing interface, a publish-subscribe interface between the applications. So we use that kind of as a way of passing data back and forth between the applications at the upper levels. And then we have two major blocks of software. We have the command and data handling software, and then we've also got the ADCS software. This is actually a joint development. Southwest Research is doing the CNDH work out at Southwest. The ADCS is being done by Charles Stark Draper Laboratory. There's some folks out of the Houston office that are doing that development. So that's worked out well for us, and that we can. It's a short trip back and forth for us to interface with each other. This is a list of all the components that make up the application software and the system software. So that's really just a summary of the various pieces. I'm not going to go into a lot of detail on that one. This is an overall view of the main data flow. We have really a single instrument in this case, which is the delay Doppler mapping instrument, which is the GPS-based instrument. And it produces data which are called DDMs. These are collected at a periodic rate at 4 hertz. The data comes and it flows in. And there's actually quite a volume of data that flows in continuously when this is in operation. So part of the overall effort is when the data comes in, we need to reduce the overall volume, and we do that by doing some compression. That was one of the challenges for this development effort. There's also some software to interface with the peak power tracker. The software actually collects some telemetry from other sensors and feeds it to the peak power tracker. So it's a kind of a software in the loop in that case. And then the ADCS component runs continuously. There is sensor data which is acquired at that 4 hertz rate. And really the whole structure of this software is based on that synchronous structure that's driven really by the ADCS algorithm, which is running at 4 hertz. So just to kind of give you a visual picture of the tasking and how this works together, this is an overall view of the 4 hertz schedule and the tasks and how they execute and interact with each other. It's a very high-level picture. And then we're also, there's also a set of interrupts which are used, so we are interrupt-driven. There's one task that's not shown, which is a background task. We have a background task which runs and scrubs the memory in the background, and so, but it's not shown in this diagram. Okay, now I mentioned one of the challenges, we're using S-band, and we have several small spacecraft with very small antennas, so we're limited on our downlink opportunities. So one of the things that we had to do for the mission was reduce the overall volume of the delayed Doppler maps that come from the DDMI instrument, to reduce that down to a manageable amount, yet preserve the important information about the storms that are occurring and the speeds of the winds and the turbulence that are captured in those images. To do that, actually, there was an algorithm which was developed. Again, this summarizes kind of the limits of the downlink. Our ground contact actually is another important thing to note. There's actually 3 ground stations that are shown here on top. There's one in Hawaii, one in Santiago, and one in Australia. But between those 3 ground stations, there's 20 minutes of time between all 3 of them together for each spacecraft. That's a very limited contact time for the downlink for each one. So initially, when they determined how they were going to manage this, there was a lot of looking into algorithms that could be used to compress the data. Another important consideration is because we have a limited contact time, well, how do we guarantee that the data, because we're switching between these ground stations, how do we guarantee the data gets down? Initially, when the mission was proposed, one of the things that was considered was the CCSDS file delivery protocol, which on more recent missions, this has become, it's become a lot more popular, and I've even seen it to the point where when the mission's spec'd out, it puts it as a requirement to do CFDP. And initially, in the early stages when this was proposed, CFDP looked like a viable alternative for getting the data down reliably. One of the things that when we got into the mission implementation that we realized there were certain things that weren't in place or didn't lend itself really well to using CFDP. One of those was these ground stations. CFDP, a lot of times people use CFDP in an acknowledged mode where you send data down in bursts, and then the ground sends up an acknowledgement to say, yes, I've got the data. The acknowledgement can be either each PDU by PDU, chunk by chunk, or when the whole file comes down. We had experience with CFDP from a mission that we recently worked on called the Magnetospheric Multiscale Mission, MMS, and we used this deferred acknowledge mode for that, so we were familiar with that. In this case, there's a delay between when the data gets to the ground station to actually when it gets to our Mission Operations Center, and the intent was to have the Mission Operations Center use CFDP. But since there was a significant delay between the ground station and the Mission Operations Center, it wasn't practical to say, we can really acknowledge this while we're still in contact. The best we could do is dump the data and then on the next pass say what was missing. When we looked at it from that perspective, we didn't really see a lot of it, a big advantage to including CFDP in the spacecraft. To keep it simpler, I mean, what we ended up with is a playback and go back and say what you've got. So playback and replay. We do have enough storage to keep several days worth of data. The storage wasn't our limitation. The limitation is really our downlink. So in this case, we'll play back for the day, and then on the next pass, we'll go back and replay whatever was missed or play back new data. So that was one of the important trade studies for the mission. Another challenge was compression. Initially in the proposal, the compression was estimated at 80-to-1 compression ratio, which was quite significant. But at that point in time, there was mention of doing this in hardware. So being on the software side of things, okay, we're thinking, okay, well, we don't have to worry about that. That's on the hardware side. They're going to do the compression. Well, once the mission moved into implementation, sure enough, that became a software requirement. And then we started to worry about it. After this turned out to be actually a several-month effort to study the compression and the types of compression that were needed. And this involved really the science team out at the University of Michigan. And what the scientists came up with is an algorithm to get the useful information that they needed scientifically from the maps. And so this describes a little bit about the algorithm. The compression wasn't quite 80-to-1, but we are closer to 50 or 60-to-1, which isn't bad. And with the sizing for the memory that we have in the downlink, it meets the mission requirements. So this is kind of a very high-level view of what the DDMI maps look like when they're processed, and what the compression that we're doing here is this is modeling a storm front, and the kind of the red section is showing the very violent turbulent part of the storm at the front of the storm front. What the algorithm here does is it's really kind of a pruning. What we do is we can calculate where that area, that intense area is, and then window out around that area. So windowing is a big part of the algorithm. And then there's some compression that's done after that to actually encode the bits and do the more conventional data compression before it's stored. So those are these two algorithms were the ones that were used on the nominal data. There's also an algorithm that's used for the background image, which really does some summing and collapsing. It turns out here what we're trying to do is measure a background level so we can average. So that ends up reducing the data quite a bit. So as part of the project, there was a memorandum that was put together that describes the compression, and we prototyped this. Actually, we used an evaluation board. This was early in the project. So we used just the Aeroflex Geisler GR712 evaluation board. But we did use RTEMS and C, which was our target language. And then based on that, we got some results. These are the times that we measured. And our target was, what we wanted to see is, how well did this fit into our 250 millisecond window. And our initial thinking for clock speed was to run the processor at 12.5 megahertz. So at 12.5 megahertz, we measured about 33 milliseconds of the 250 millisecond cycle to run the algorithm, which was promising. That met our requirements. Now, it turns out that another decision that we made in the mission, initially we had considered running both cores of the processor at 12.5 megahertz. And one of the things that we found was we did a trace study to determine if we would rather do that or run a single core at 25 megahertz. And we opted actually for the latter, to run the single core at 25 megahertz. It simplified things greatly in terms of how we had to set up the cores, the coordination that we had to do between the tasking. So it made the overall structure of our software simpler by doing that. That's it. Questions? Got a couple.
I'm just curious, what was the reason why you guys were so limited on ground station resource?
Well, part of it is in terms of the budget of this project. It's a Class D mission, so it's very limited in terms of, I mean, in order to get timely ground resources, you have to pay for them. We have 8 spacecraft and a lot of data, so negotiating more contact time was cost prohibitive for us. So, and you know, it turns out the useful data is really the part that we're compressing out. So we don't really have to transmit all of that. We could get, there's times when we do transmit raw data initially when we're in commissioning, but for the majority of the mission, you know, we don't really need all of that data.
If you had more, would you have been able to do more with the mission?
I'm not sure that it would help this particular mission. I mean, our focus is very, very narrow here. I mean, the intent of this mission is to give information about these storms that we don't already have. The meteorological satellites that we have now actually do provide better resolution, you know, for a static image when they pass over, but what they don't have is they don't have information about how violent the storm is and timely information. So the focus here was on timely and you know, to fill in that other important piece of the forecasting.
Okay, great. Thank you. Robert, I had some general questions.
Okay.
So is this a NOAA mission, or is it who heads this mission?
This is it's a NASA funded mission. It's out of, I believe it's out of Langley.
Is the data archived at NOAA, or is NOAA involved in any way with this?
Not that I know of.
Okay.
Not that I know of. But I may be limited there. That's a question for Scott. He may know more of that.
This is actually really simple. So was the clock rate of the 712 affect the power supply? Is that why you clocked it down?
Well, it's part of the overall part of the overall power budget, and we could run the 712 at 25 and maintain about the same draw, or we can run both cores. And so we opted to go with the 25 megahertz and run a single core.
Because I know when we've done the S&P, so far we haven't found a processor that using the second core actually adds any measurable power. I've talked to other RTOS people who say the same thing. So apparently the dual core doesn't really, you can't shut it off, so it doesn't really matter. But that's a different design issue.
Yeah.
So it's the clock rate driving the power budget.
Right. I mean, we could actually operate the we could actually operate both cores at 25. Initially, we were scoped out at 12.5 for both cores, but based on the timing, we only need to run one core, and we're not running the SMP version of RTEMS. The development on this started, I think, before that was available. Yeah, and so I think the decision to run a single core was more to simplify the architecture. You know, there is power concerns. If we can't go up to 50, for example, but we can go up to 25.
Is your yes? Okay. Is your Star Trek a standalone unit, or do you just use it as a head and do the attitude calculation within your, what was it called, your processor part? Do you do that calculation yourself?
I'm sorry, I missed the first part of your question.
The Star Tracker is a standalone?
It's a standalone.
So it already delivers an attitude quaternion or something like that, or?
Yes.
Okay.
It delivers. It delivers a frame and but it does have a coordinate in it.
Okay, thank you.
So it simplifies things.
And one small note: for this mic, we're always going to leave it on. The audio volume is controlled from the booth, so don't feel the compulsion to press the button.
I had a question about the way the software came together, was integrated. I think, if I recall correctly, in the architecture slide you had, there was a software core layer atop which there were, I think, a C&H kind of component and a ACS component, both of which were delivered by different organizations.
Right.
I was wondering if you could talk a little bit about the heritage of the core layer. Was that we're using the Goddard CFE, or were you using an in-house version? And in general, was there something inherent to the architecture that facilitated the integration of the software, the applications from different organizations, or basically do you have to take software deliveries from, I think it was Draper, you said?
It was with Draper.
Yeah, and Rapid and things like that, or did that just cleanly plug in based on the architecture that you're using?
Well, in this case, we have a fairly simple interface with Draper, and we actually provided the maybe even more so, the interface with Draper isn't through the software bus, although they're familiar with the software bus that we have. Initially, several years ago, we worked on a proposal with Draper, and we developed a software bus for a demonstration that we put together for part of that proposal. This was actually before CFE was made available, before it was open. It was made available through SourceForge. But the component that we have, it's fairly scaled down in terms of what it provides. It really just provides a buffer pool and a way to publish and subscribe to share data without doing so many memory copies. But we built software on that architecture for the past few missions. So we've become comfortable with it, and we've started to organize our software that way. It's similar to CFE, but it's not CFE based.
Well, thank you, Robert.
Thank you.